First of all, why we study seawater uranium extraction. First, for uranium energy to remain a sustainable energy source, there must be assurance that economically viable supply of uranium is available. And seawater contains 4 billion tons of uranium. It's a dissolved uranium in this case. It's unlike the land ore, you need to break out the solid bonds to using strong acid. But in seawater, they already dissolved by Mother Nature. So we just harvest it directly from seawater. And this unconventional resource combined with a suitable extraction cost can potentially provide a price cap and ensure centuries of uranium supply, even with aggressive worldwide growth in nuclear energy application. So in this case, we have almost a sustainable uranium resource for nuclear energy to deploy. But the challenge here is the low concentration of uranium in seawater. It's only at 3 ppb level, exactly 3.3 ppb, if you correlate to the salinity. In the 1990s, 80s, 90s, the Japanese spent a lot of money to study this technology. This is not a new technology to extract uranium from seawater. Back in the 60s, the US and the other European countries have looked into this problem already. Back then, they are using some kind of titanium oxide, using a pump and treat kind of process, which costs a lot of energy to produce uranium. But the Japanese create a kind of generate a new technology called the mooring collection system. I will introduce to you just in the next slide. Basically, this mooring technology is you deploy the absorbent material in the seafloor, and then let the seawater current to bring the uranium to the sorbent material. So in this case, we limit the pumping process. We limit the labor costs, technology costs. From the Japanese study, we find out that almost 69% of the technology cost comes from the absorbent material. So our research focuses on absorbent material development. Here's the technology description on the screen. You can see it. On the upper left side, you can see the preparation scheme of grafting absorbent material. The Japanese using electron beam, E-beam, or gamma ray to irradiate polymers to generate some radicals, and then incorporate some monomers and then a functional group, and then produce this sorbent material. Then they deploy it in the seawater. In this case, they deployed it in the Okinawa site. After 30 days, they just harvest this material and let it float to the surface, and then they collect and extract out uranium from the system. So again, the beauty of this the mooring system is not using pump method. Instead of just let the seawater current to carry this material to the system. So DOE started the seawater uranium recovery program in fiscal year 2011. So our team seeks to take advantage of recent development in high-performance computing and advanced characterization instruments, and the nanoscience and nano-manufacturing technology to enable technology breakthroughs. We try to emphasize 3 areas. One is synthesizing novel nanoscale absorbent material with architectures tailored for specific chemical performance. In this case, we try to design molecules which can target uranium only. In this case, we can selectively absorb uranium from seawater. The second item is applying quantum beam technology to understand dynamic chemical process at the atomic and molecular level. In this case, we want to better understand what's happening on the surface, why some elements absorb strongly, some elements absorb weakly. So then we can begin to manipulate the surface, then we can increase the absorption selectivity and capacity. The third item is simulating and predicting structure and functional relationship using modern computational tools. So in the past 20 years, we see the fast development in quantum in the computer science. So in this case, we want to take advantage of it. Our goal eventually is to develop an advanced absorbent material that can simultaneously address absorption selectivity, capacity, kinetics, and reusability, durability, and to reduce the technology costs and uncertainties. So we want to address these 4 factors at the same time, instead of at the expense one of the other. So in this case, we don't want to increase the capacity but decrease the selectivity. That's not ideal. So we want to address all 4 of them at the same time. Here's the research areas for this call. So we have totally 7 areas. The first one is the uranium coordination, computer-aided ligand design and screening. The second area is thermodynamic kinetic structure characterization. The third is advanced absorbent material using radiation grafting method. This is a so-called Japanese baseline technology. And then we also encourage people to think outside the box using novel nanosynthesis. So in this case, we can increase the surface area. And the fifth one is marine testing and performance assessment. Once we have the material developed, we want to make sure it performs well in the marine environment. And then the sixth one is the long-term durability and reusability. So we want to recycle, to repeatedly use this material over and over again, so then we can drop the technology cost. And the last one is technology cost analysis and deployment model. So in this case, we want to emphasize which technology components is the driver for this technology cost, so then we can feed back to our research area. I give you a couple examples in the following 4 or 5 slides here. The first one is understanding binding structure and the mechanisms. We understand uranyl bind with tricarbonate in seawater, with the counter ion most likely be the calcium or magnesium. But what exactly the binding mechanism for uranyl in seawater, we want to know that. Thanks to our X-ray diffraction studies, we identified that's a theta 2 binding, that's 2 binding sites there. And then also we find out for the development used by Japanese is the aminodoxin functional group. We find out a cyclic aminodoxin functional group binds stronger than the open structure. So we now know that. I list a couple publications there in the recent studies there. And then once we armed with the knowledge of this binding structure and the coordination mechanisms, we can use the modern computer science computation tool to help us to select different functional groups into this process. In the past, you can select probably one functional group or one kind of ligand. You can do some calculations by hand. But now using computer, they can do in minutes. In the past, you may take a day or 2 or to do the computation. Now computer tool can help us to do very fast. So we can try hundreds or if not thousands of different combination of functional groups. In this case, we can select the best functional group coordination geometry for uranium selection. And then the other example I gave here is the kinetic and thermodynamics. In this case, you can see we use the entropy study to suggest the overall complexation is endothermic process. That means if you increase the reaction, the temperature, the reaction will favor to the product. In this case, if we increase the seawater temperature, we expect to see a higher absorption capacity. So that's what we validate through fundamental understanding to the field study. So we correlate that relationship. So I also give a couple reference down there too. And the third one I gave is here is the so-called Japanese technology using radiation-induced polarization process. In this process, we basically focus on 4 steps. The first is the irradiation of trunk materials. The second is grafting the monomers. And the third is functional group conversion. And the last one is the alkaline conditioning. So we focus on this 4 process. Most importantly here, give you an example. The Japanese using probably about 20 to 30 micron size fibers, but we find if you decrease the fiber shape or fiber size, you can increase the surface area. Once you have a higher surface area, then you can have a higher surface functional functional group cooperating into the surface area. Then it would lead to a higher absorption capacity. So that's what we have been doing in the past 3 years at the Oak Ridge National Laboratory. And another one is technology cost analysis. So what we try to do here is try to assess technology cost potentials. For example, we want to identify highest impact component of the system. Then we can guide or prioritize our R&D research effort to reduce the cost. And then we can also want to establish a technology threshold. In this case, if we can identify the technology of uranium extraction from seawater at whatever price level, for example, 300 level, then we'll just make sure we'll have unlimited supply of uranium at $300 per kilogram uranium. That's our goal. For example, I give here in the box here is JAE, a Japanese colleague. They studied, based on their analysis, it's about $1,000 per kilogram uranium back in the probably 1990s. And then in 2011, when we start this program, we analyzed the Japanese data. We find that for US, using similar process we deployed in the US, it's about 20% more, higher. It's about $1,030 kilogram dollar per kilogram. But after 3 years study, we already, from the Japanese 1 gram per kilogram absorption capacity, we doubled that in the past 3 years. Fortunately, thanks to our research at Oak Ridge. Now our technology cost is 610. So if you double the absorption capacity, you reduce the technology cost in half. We'll continue to increase the absorption capacity. We hope to drop the technology cost to a reasonable level eventually. And then the last example I gave here is marine testing. We want to determine the performance of the sorbent materials. In this case, variables we want to study is salinity, temperature, flow rate, total organic carbon, and other trace elements. We have a marine testing site at Spring, Washington, under the Pacific Northwest National Laboratory. In summary, so we started this program in 2010, and our strategy is to develop a novel absorbent material using high-performance computing, advanced characterization instrument, and nanoscience and nanomanufacturing technology. The second is achieving molecular-level understanding of ligand coordination model, absorption mechanism, kinetics, and thermodynamics. So we also have economic analysis trying to guide the technology development. So with your help, we can continue to improve absorption capacity, selectivity, kinetics, and reusability. So we expect the technology will continue to, the cost of technology will continue to drop. With that, I thank you for your attention. Thank you for tuning in for this program. If you have any further questions, feel free to contact me at my information is listed here in the first top page.
Is there any interest in inorganic adsorbents? These will perhaps be more stable in marine environments.
Yes, definitely. We are interested in organic materials, but the key is how to deploy it. We want to make sure there's a deployment. If you can find a way for the inorganic material can be deployed in the real ocean environment, we welcome that idea. The key here is we don't want to pump the seawater. If you pump the seawater, you may generate, the cost is too much, too high. We cannot afford that.
Is the fuel resources focused exclusively on recovery from seawater?
At this time, yes. Our focus is seawater uranium extraction.
What is the uncertainty of the uranium price that you quoted in your presentation?
Yeah, the uranium spot price, if you know, you probably know but very well, this fluctuates quite a bit. After Fukushima is dropped to a historic low, so now the current spot price is about $100 per kilogram. That's extremely low at this time. But we will consider this a long-term research, so to ensure the sustainable future of nuclear energy. Because even though the technology for mining uranium from land ores, you will start to see the price will increase eventually. But this is a technology our goal is to provide a cap on uranium price. So in this case, if we can cap at 300, even though that's still much higher than the current uranium market price, but we know at that price we have a limited supply of uranium for nuclear energy deployment. That's our goal.
Are there any specific adsorbents identified or developed that should be focused on?
No. We are focusing now on aminodoxin functional group. I give you in the example here. But if you have other good candidates, ligands, please make that proposal to us, and then we'd like to hear about it.
For computational design and simulation, is teaming with an experimentalist required?
It will be definitely beneficial if you're teaming with experimentalists. In that case, you can really, after you do some calculation, you can validate your data, your model. That's very important. Yes, I would say encouraged, not required.
Is there guidance for the cost of the adsorbent?
The guidance of the cost of the we have a team to study this cost. So if you have a question about cost, I can give you the contact information. The guidance here is we want to use the so-called Japanese technology as a reference technology. So we want to use any materials that's not expensive, more expensive than the Japanese reference material. Even though newer materials, eventually after a couple of years development, we will do the evaluation to see how much that technology costs. We are doing that for some of our advanced materials.